Matrices. We're going to talk about how matrices work, how we do operations with matrices. Matrix is the singular, the plural is matrices. This is one of those times where the Latin comes down to us and is preserved to some extent in English. Matrix and matrices is the plural. A matrix is a rectangular array of data. If you've heard of the movie Matrix, maybe by the end of today, you'll figure out why it's called matrix. So it's a rectangular array of data. It's arranged in rows and columns. Each individual item, each number, or numbers, is called an element. And we say the dimensions by saying rows first, columns last. Rows by columns. So if there are 2 rows and 3 columns, it is a 2 by 3 matrix. A matrix is just a chart or a table that doesn't have the labels. Here's an example of one of them. This has 3 rows, 4 columns, so it's a 3 by 4 matrix. 3 by 4, that's the dimensions of the matrix. 2 is the element that is located at row 2, column 3. Row 2, column 3. That's how we identify it. You have seen this type of terminology before. If you think back on Excel or other spreadsheets, when you click on the cell, up at the top of the page, there's usually a line that says where you're typing and shows you're typing, and at the front of it is usually a notation like this, R2, C3, row 2, column 3, to let you know where you are. Adding and subtracting matrices isn't really hard. First off, you're not going to do much matrix operations to speak of. When you want to do anything of any significance that has matrix in it, you're going to be using a computer, but you do need to know how to do it, how it works, so you'll understand the operation of what the computer is. You have to be smarter than the computer to use the computer. Okay, adding and subtracting. The add-ins, the things that are added, must have the same dimensions. So this is a 2 by 2 matrix. This is a 2 by 2 matrix. They can be added. If they have different dimensions, you just can't do it. Addition of matrices is commutative. That means the order doesn't matter. No other operation is. Addition is the only thing that you can change the order. You're accustomed to being able to change the order in multiplication, but you cannot. It must be done in the order. It's not like other types of multiplication. How will we do it? We'll add and subtract, or subtract, the corresponding element. So here's row 1, column 1, plus row 1, column 1, 5 plus 1, is placed for the answer in row 1, column 1. So row 1, column 1, plus row 1, column 1 goes in row 1, column 1. Then row 1, column 2, negative 3, plus row 1, column 2, 2. And the answer goes in row 1, column 2. And so forth till you get all of the elements of your answer matrix. Addition is pretty easy, pretty straightforward. Here is an example of using it on the coordinate plane to do things. This is another type of representation with regard to a translation. Here's a matrix that represents this point. Again, matrices don't have labels. Whenever we represent points in matrices, it is our convention to make the top row X, the bottom row Y. And you need to stay with that, because all of the things we'll be doing will assume that the top row is X and the bottom row is Y. Don't switch it to be columns or some way different. A translation matrix means the change that you make to it. So what this is saying is we're going to subtract 1 from each of the X values, and we're going to add 3 to each of the Y values. We place here the translation matrix. We always put the translation matrix as the first one, although it doesn't matter with addition, but we put it first to be consistent. So this means we'll subtract 1 from each of the X values, which are on the top row, the value for A, B, and C, giving us the value in the answer matrix or image matrix as A prime, B prime, C prime. We'll do the same thing for the y values, adding 3 to them. So the result is a shift back 1 and up 3. This is another way to write the translation. You'll recall that we did the mapping way to write it. The mapping would say it's a mapping from xy to x minus 1, y plus 3. The vector way to write it would be -1, 3, showing what happens to each one of them. Now these things aren't consistent across everything, but this will get it the idea of how we're doing things for this course. The next is scalar multiplication. Scalar multiplication, or multiplication of a matrix by a scale factor. Scalar is the adjective that comes from scale. Scalar multiplication is not really a big deal at all. Scalar multiplication is just, distributive property on steroids. So let's look how that would look. Say we have this matrix, and we multiply it by a scale factor of 2. It's just the distributive property. We multiply each of the elements by 2. No big deal. We always put the number first. I guess it would work if we didn't. Notice that our original matrix is a 2 by 3 matrix, and our answer matrix is also 2 by 3. So it works out well that way. Okay. Now, multiplying matrices. This is the problem. This is the bugbear that gets everybody. This is why we like computers. So multiplying matrices. Multiplying matrices, multiplying is not commutative. The order in which they're written matters. The dimension, this is kind of weird, and when I do it, it'll be a little bit easier. I'll go through it, and then I'll show you, and it'll be a little clearer when I go through it. Okay, so the dimensions here when I show it to you. The middle two numbers, so if I'm going to multiply a 3 by 2 matrix times a 2 by 4 matrix, I can. If the column of the first matrix is the same number as the row of the second matrix, then I can multiply it. If they are not the same, I can't do it. The resulting matrix will be the leftover numbers. It will be a dimension of 3 by 4. So I can multiply a 2 by 3 and a 2 by 4, and my result will be a 3 by 4. I'm going to multiply and then add. I'll show you how that's done. So I'll start with the matrix. And I want to multiply it by this one. Let's see if I can do that. Okay, the first matrix is 3 rows and 2 columns. It's 3 by 2. The second one is 2 rows and 4 columns. The center is the same. The number of columns in the first matrix, 2. The number of rows in the second matrix, 2, is the same. Therefore, I can do it. And my resulting matrix will be 3 by 4, which is the rows of the first one, the columns of the second one, the numbers that were not in common. So let's look at how that works. It's a pain. The first thing we'll do is multiply the first row, row 1 of the first matrix, by column 1 of the second matrix. That's why those numbers have to be the same. How do we do that? We multiply the first elements, we multiply the second elements, and we add the results. 1 times 1 is 1. 2 times 3 is 6. 1 plus 6 is 7. That was row 1, column 1, and the answer goes in row 1, column 1. Then I'll do row 1, column 2. One times negative 1 is negative 1. 2 times 0 is 0. Negative 1 and 0 is negative 1. This was row 1, column 2, and it goes in row 1, column 2 of our answer matrix. Do it again. We'll have row 1, column 3. And the answer is going to go into row 1, column 3. So let's do that one. 1 times 2 is 2. 2 times 1 is 1. 2 plus 2 is 4. Same for the next one. Row 1, column 4. 1 times 0 is 0. 2 times 2 is 4. We go on to the next row. You can see that this is a lot of fun. So now we'll do row 2 times column 1. That's 3 times 1 is 3, 4 times 3 is 12, 3 and 12 is 15. So go ahead and finish that out. And when you do, you should get this. How that will work. Let's look here. Can we multiply these two, which is asked to do? Yes, we can. This is 1 by 2. This is 2 by 1. We can multiply. We could not add these if we were asked to because the dimensions are different. This is subtraction. Can we subtract them? Yes, we can. 2 by 2, 2 by 2, individual elements. Our resulting matrix will be 2 by 2. Could we multiply these two if we were asked to? Yes, because the columns, the number of rows here, the number of columns, and the middle numbers, the number of columns here and the number of rows here, are the same. Will this multiply? Yes, it will. This is 2 by 3, the number of columns is 3. 3 by 2, the number of rows is 3. That's the same. And our resulting matrix will actually be smaller. It'll be 2 by 2. Okay. And here in this particular lesson, the matrices.